Here's a problem that has to do with the uncertainty principle, Heisenberg uncertainty. This one doesn't lend itself much to a drawing because what it says in trying to pinpoint the position of an electron, the uncertainty in position is reduced to 5 times 10 to the minus 12 meters. So am I going to draw you a picture of an electron? It's as if I know what an electron looks like. Sure, here's an electron. It's moving at some speed. Okay, good. What we know about it is we've reduced its uncertainty in position. And how do you do that? Well, you got to bounce things off the electron in order to find out where it is. So if you can reduce its uncertainty in position, you can say that the delta x is 5 times 10 to the minus 12 meters. As we have it localized within a small volume, 5 times 10 to the minus 12 meters. Terrific. So what does that imply? This Heisenberg uncertainty principle says that the uncertainty in position multiplied by the uncertainty in momentum is greater than or equal to h over 4 pi. H is the Planck constant. Swell. We can solve this mathematically. I mean, it's not a big deal, right? Simple looking equation. We know what delta x is. We're trying to find out what delta bx is, and we know all this other stuff. It's just numbers. So what do? We solve it algebraically. It's not much at all. Delta x is greater than, delta px is greater than or equal to h over 4 pi multiplied by delta x. So we just put that all in, and we crank out a number. The number says 1.06 times 10 to the minus 23 kilogram meters per second. Okay, is that reasonable? What do we know from electrons? They're way too small for us big clumsy oafs, so we're never really going to get there. However, there is a little something we can do with this. If that's what delta px is, what's px? What's p? In this case, it's momentum, it usually is, and so you can say then that this is m delta v in the x direction. It's the same thing as delta bx, and m delta vx is this greater than or equal to 1.06 times 10 to the minus 23 kilogram meters per second. Does that help us much? Well, yeah, because we happen to know what the mass of an electron is. The mass of an electron, we know, is 9.11 times 10 to the minus 31 kilograms. So if we put that in, this tells us what our uncertainty in velocity is. And here it is. Delta of v is 1.16 times 10 to the 7 meters per second. Now we're somewhere. What's 1.16 times 10 to the 7? 10 to the 7 meters per second? Whoa, this is fast. Speed of light is 3 times 10 to the 8th meters per second, so this turns out to be 3.86% of the speed of light. That's the uncertainty in the velocity. If we have this as the uncertainty in position, this being 5 times 10 to the minus 12 meters. So what's the size of that? Well, it's getting down a little bit below the size of a hydrogen atom. So if we have the electron localized within a hydrogen atom, some part thereof, it means that our uncertainty about the velocity is huge. So therein lies some difficulties. There are some things we don't seem to be able to know based on the way quantum mechanics works. So are there things that physics isn't going to be able to get the answer to? So far, it looks that way. Okay.